Section 20.13, RC circuits. You may have heard of a device known as the pacemaker, right? It's shown here where there's an enlarged heart or an x-ray of a heart, an electrical wire that's connected to a pacemaker that's been installed surgically in this person. What does a pacemaker do? Well, it keeps a heart beating regularly, right? But how does a pacemaker keep pace? How does it know what a regular heart rate is? Turns out you can tell it what a regular heart rate is using your electric circuit knowledge, something known as an RC circuit. So let's take a look. An RC circuit is a combination of a resistor and a capacitor wired in series and connected to a voltage source, like a battery. And it turns out when you have this combination, the capacitor isn't going to instantaneously have its maximum charge Q. It's going to take some time to get there. And so that's what this equation shows. The capacitor charging equation shows that the amount of charge at any given instant on the capacitor plates is equal to its equilibrium value, the final value that it reaches, times the quantity 1 minus E raised to the negative time divided by RC. And RC here is the resistance times the capacitance. It's known as the time constant because that's what sets when it has reached a certain fraction of the charge, of the final equilibrium charge. So you can see the final charge is shown here as Q0, and that's equal to the capacitance times the total voltage, V0. And as the capacitor charges, it follows this equation where the Q increases from 0 up to this final value. So the Q0 here is not actually an initial value, it's more of a peak value, a peak amount of charge. So this is how it can charge up. What about the other side? Well, that's when you close the switch, it charges up. When you open the switch, the capacitor can then act as a battery, and it can create its own current. So charging, we have the current coming from the positive terminal of the battery through the resistor to the capacitor. What about for discharging? For discharging, we don't need a battery anymore. The capacitor is acting as the battery, and where there is positive Q, that's now acting as the positive terminal to create a current that flows around to the negative terminal of the capacitor. And the discharge equation of the capacitor is a little bit simpler. The charge at any given instant in time is equal to the peak charge times E raised to the negative T over RC, where RC is again the time constant. That sets the amount of time it takes to discharge to a certain value. And we can note here, here's a nice plot of how the charge varies with time. When you're discharging, you start out at the max value, and then you have this exponential decay. And you'll see an example in the homework where you get to solve a problem with this that shows how this relates to a pacemaker. The pacemaker, you can set the resistance and the capacitance so that at a certain time constant, when it's discharged to a certain amount, it will automatically then kick in again. That tells it the amount of time to pass before sending another pulse to keep the heart beating in time. If you don't like the medical examples, another example of this is with your windshield wipers of your car. There's the variable windshield wiper where you can go from slow to fast depending on how you twist the knob. That's because it's tied to a variable resistor. So as you adjust the knob, you're adjusting the resistance, and so you're adjusting the amount of time between the windshield wipers going and pausing. You're able to set the time constant, which is pretty awesome. So that's RC circuits in a little bit of a glimpse. Very cool applications and not too bad at the math.